welcome to our podcast. My name is Lila.
And I'm Nikita.
We are part of BiodeCCodiNNg, a European doctoral network focused on decoding novel enzyme-catalyzed chemical reactions. Today we are excited to talk about green chemistry, where science meets sustainability.
We are honored to have a true innovator with us today, Dr. Pablo Domínguez de María. With over 150 publications and his work in academia and industry, he has a profound impact in the field of biocatalysis and sustainable chemistry. He is also the founder of Sustainable Momentum, a consultancy firm in the field of industrial sustainability. Thank you for joining us today.
Hello, hi, it's a pleasure to be here.
So let's already start with the basics. For initially our audience to understand, can you explain what green chemistry is and how significant it is in this age of time?
Thank you. This is quite an important question, and I think it's the first question to answer. We need to think that all materials that we use in our life are made of chemicals. These chemicals are made in chemical industry through a lot of synthetic processes. And chemistry in the processes generates residues that we need to treat, a lot of chemical residues. And since we are a lot in this world, a lot of people, and we have many chemical processes, the amount of this waste that is being created is quite huge. So we need to find alternatives to make this synthesis of products in a greener way. So green chemistry is a discipline that is trying to bring this option. It is a branch of chemistry that I think started more or less 40 years ago by some people started to define which are the principles of a green chemistry. And over the last year is being more and more important, and you need to know which is the waste that you're making in your process, and then via the green chemistry principles and strategies, try to reduce the waste that you are making in your chemical systems.
That is fascinating. We also use in our PhD projects these principles, catalysis, waste management. Can you explain a little or elaborate a little about what these principles are?
Yes, green chemistry is based in general terms on principles, which are the rules that you in principle should follow when you create a chemical process. The first and most important principle is waste prevention. This is why it's the first one. So the concept is it's better not to make a waste than then create a waste and try to treat it, of course. So waste prevention is at the core of a green chemistry, because if you develop a process that is generating less waste, you will have less problems at the end. Also, catalysis is another green chemistry principle, because when you use a catalyst, you add something in the reactor that is going to accelerate your process, is going to make it more efficient, and this is going to generate less waste at the end. So we have other green chemistry principles there, trying to use other resources from biogenic sources and so on to try to make a greener system at the end.
Yes, that would be impressive for applications.
Sure, of course.
We also, from your research, know that you highlight there is a difference between primary waste, for example, solvents in wastewater, and secondary waste like CO2 emission. But we would like to know more why this distinction is so important.
Well, we need to think first that what is created in the reactor is the waste that you create by the use of water and by the use of the organic solvents. So those are the two main wastes that you're making. And traditionally, green chemistry measures the impact of these two solvents, wastewater that you make, and then say, okay, you are creating this liter of wastewater or this liter of a solvent. The point is, this waste in chemical industry today is treated before it's sent to the planet. So if this is going to be treated, you're not going to see this waste in the planet, but what you are going to see is the residue that you can create when you treat this waste, and this is CO2. You have to invest energy and fuel to make your process to treat your waste. Your waste is going to disappear, but you are going to leave the CO2. So at the very end, the ultimate waste that is going to stay in the planet for a chemical process is the CO2 that you are making in the first waste. This is why it's so important to make this separation between the waste that the first primary waste you generate from your process and the one that is going to remain in our planet, in the atmosphere, and it's the one that in principle we should take more care of.
So you said that we are making the planet more sustainable. We are moving towards greener conditions. And how do we actually know that a process is green, or how do we do a matrix to analyze if it is green?
Yeah, of course, in all senses, I mean, in all processes, you need to measure what you are getting to be sure that you are getting maybe first a green process or in second term a greener system than the previous one. You need to determine which is the ways that you are making. There are some alternatives or metrics that have been put forth for this system. I think we will discuss a bit in this conversation. And based on that, you can measure what you are producing, and then you can say, okay, my first process started with a waste of this amount, and then by improving, optimizing things here or there, our waste production for the same process is now less. And our aim is to try to reduce this even more to get a better process system at the end. This being said, the main issue with the green chemistry is that there are many angles from which you can see what is green or what is not green. You might measure in CO2, as we said before, which is something that is quite important, but also we can think in toxicology of the things that you are using, and this is not measured in CO2, so you also need to measure how toxic, how explosive is something for when you are using it. So there is a combination of things here to try to make in a holistic way what is really a green process. But at least from the beginning, for academic work in industry, in the lab scale, I think make a measurement of the mass metrics like CO2 makes a big impact and big indication from where you should go with your process.
As you mentioned earlier, catalysis as one of the key principles of green chemistry, and since we are also our research focuses on enzymes and biocatalysis, could you break it down for our listeners what exactly are enzymes and what makes biocatalysis a more sustainable alternative compared to traditional chemical processes?
This is a good question. I started my discussion by saying that all chemicals we use are formed in a chemical process, which is true. The chemical industry will make a process. Now in nature we have the same, but it's not called chemistry, it's called biochemistry. Means that all the things that we are based on chemical reactions, which are biochemical reactions. And of course, nature had to find this catalyst able to accelerate and to make these reactions at room temperature we have in this planet. And these catalysts are what are called enzymes that we are using now. And then there were people many decades ago that started to think, okay, if these catalysts are so efficient in nature, why don't we try to put them out of context? Why don't we get them from nature and put in a chemical reactor and see if we can have a benefit of these enzymes to make a greener process, because of course conditions in which enzymes are working are very mild. And this field is the field that is called biocatalysis, the one that you are working now, which in general sense tries to use these natural catalysts to make chemical processes in a greener way. But at least on paper it's intended to be this way.
And can you share an example of real-world application of using biocatalysis?
I think that there are quite a lot of industrial cases at this moment using what is called industrial biocatalysis. I think it has boosted quite a lot in the last 20 years. There were some cases before, but now there are continuously new processes, new approaches being done. If I had to pick one that I think is quite interesting, is we have some antiviral compounds that were needed for the COVID time, molnupiravir, islatravir, and so on. These compounds, it was quite urgent at this time for the society, for the global society, to have these tools and these drugs available for the society to cope in the extreme cases of COVID. And people started to work in biocatalysis. Those are complex molecules, so they need quite a lot of steps in chemistry to make them. It's not trivial. And they managed to make some biosynthetic synthesis of these molecules using enzymes biocatalysis, in a matter of months. So in a matter of months, people were able to produce this in a mass scale to be used in the world. So I think this is a nice example, quite recent, that also is reflecting the need of having things in a rapid way to implement processes that can be used for the world.
So every process has some bottlenecks. What are the main challenges that researchers face while developing biochemical processes?
Well, we need to go back again to what is an enzyme and what is biocatalysis. So an enzyme is a catalyst that is evolved in nature to make a reaction under some specific conditions. And these specific conditions in which this enzyme is doing the best work are not the same as the conditions that you have in chemical reactors, where you are intended to make more product per minute with less solvents, less water, and so on. And then, of course, you have to adapt, because you are putting this enzyme out of concept, of context, to put it in a reactor in which these conditions are not the ones that they had at the beginning. And then you need to adapt and tailor this enzyme to make the process run in these conditions. And this is always a challenge, because there is a need to find the right catalyst that can compete in the right conditions. It always takes time. And then, of course, we need to address whether the economics of the process is going to be also in the right side. If it's not, you might have a very nice process, but industry will never take it as a case for the synthesis.
And most of these reactions happen in water, right?
Right.
And water is often considered a green solvent, but does its use pose some challenges in the waste management at the end?
Yes, indeed. I mean, we need to think that if we do the reaction in water, the residue that we are going to generate is wastewater, is what is called wastewater. So it's not the water that we can drink, we can treat it as a normal water. We have to treat it, remove all the chemicals, byproducts, all this stuff that we have before we can use this water again. Then, of course, if you consider the volume of molecules that you are making in this world, and start to do the math, you realize that we will need many liters of water to make these chemical processes. And we know that in this planet, water is one of the scarcest things at this moment. The access to drinkable, edible water in many places is hard at this moment, it's difficult. So one has to keep in mind how to combine the two things, how to use maybe water as a solvent that can make organic reactions in a mild way and in an efficient way, but at the same time how to treat this wastewater that you are making to be sure that we can have an holistic cycle in which the water is being used, being treated, recycled again. And this is easy to say, but when you want to make it or to implement it, in some cases it's complicated. You need to really to make an integration and in-depth study of everything that you have there.
So this treating water also not an easy task. So wastewater treatment itself generates CO2, right?
Yes.
What are the strategies that you can reduce these emissions?
Well, I think the best way to treat the water would be that you can send all your residues to what is called wastewater treatment plant, which is a place in which you have a consortium of microorganisms that are able to digest, to remove all the chemicals that this water has. Now, the problem is that in some cases this works because this consortium can treat these chemicals, but in some other cases you are making chemicals that they cannot be treated. So in this case you need to make some pre-steps to remove all these chemicals before you can send this effluent to the wastewater treatment. Every step that you are putting, you need to put also invest energy in the system. And if you invest energy in the system, you are going to generate CO2 because you have to create this energy from some sources, and then this is going to be the CO2 that you are making by treating this wastewater treatment. In the worst case scenario, you will have to incinerate the water because you have some chemicals that they are impossible to remove from the water, and microorganisms can't cope with them. And then the CO2 you are making is even worse, because when you have to put fuel to burn it, an amount of water, you are going to produce more CO2. But this now is tabulated by industrial people in Novartis, that they came up with some industrial data. And this is, in principle now, is feasible to measure and to make an estimation on the amount of CO2 that you are making with your volume of system. And then more or less you can know where the better conditions for the treatment are.
And since we are already talking about the topic of waste treatment, there are some other major global challenges, and we want to talk about what sustainability and green chemistry has an impact on them. For example, CO2 emission, climate change, resource depletion. These are some major global challenges, and can you also explain a little bit?
Yeah, well, we have to keep in mind that this picture is complex. It's not that we make only one effect and then we create a green solution for the things. The CO2 angle is one of them. Quite important, we know, I mean, this is related and not as a coincidence, it's called as global warming potential. So the more CO2 that we have in the atmosphere, we have a higher temperature and changing climate. But also, if we want to be holistic in sustainability, we need also to think about other things that are there that are quite important too. I can put an example. If you are using a land to make lignocellulose, to make biomass for the chemical industry, every hectare of land that you are taking to make this has to be removed from other things. I mean, it could be a rainforest, but it's removed. It could be place in which the animals are being fed and grown. It could be a place in which you had, I don't know, a mud or something. So you remove this from there, you are making an impact, and this has to be considered too. Not to mention, I mean, if you also work or think in food industry, you add all fertilizers, chemical fertilizers. This is not done because of people liking to do this. It's because if you want to feed the increasing population we have in this planet, we have to do that to improve the productivity per hectare that we have. And all these chemicals are going to have an impact in production first, and then when they are in the soil. And this is also another impact that in many cases maybe it's not as clearly seen as the CO2 or as the contamination that we can make in other places, but it has also an important impact. So at the very end, I think the best way to go is try to be holistic and try to look at the big picture from all the places, and then try to find the process that is impacting less in most of the places, knowing that this is a real challenge. So it's not something that we should skip from saying that green chemistry or sustainability can be quite easily reached or something. There are fundamental challenges in making chemistry with less input when we want to do it in a massive way. So we have many angles from which we to think in sustainability.
And what do you see as the future of green chemistry and biocatalysis? Do you think emerging technologies like AI, automation could make biocatalysis even greener?
Yes, I think so. I think maybe the most important part now is that the awareness of being green and trying to develop more sustainable processes is there. So I think this is going to act as a triggering factor to bring the things. This being said, there are also some things that can be used and applied. One is the introduction of renewable energy in chemical industry. If we manage to link all the energy that we are using in chemical industry with more renewable resources, we are going to generate less CO2 from this system. This is also going to have an impact. And automation, of course, is also going to have an impact in the sense that many processes, many steps of these processes probably are going to be done in a more efficient way. At the very end, we should consider that measuring with the metrics how green or ungreen is a process is not to give a value that this absolute value we make this CO2, for instance, and this is, but it should be seen as a place from which we can, or we should try to improve the things. So we are making 100 kilos now. Our aim is next year or next 2 years trying to reduce this to 80 of this process. And then if we find a new breakthrough that is coming, new reactor system that can save you some reaction time, new enzyme that can do the things in a more efficient way from 80 to 60, and then trying to always in all processes trying to be so with this view on trying to be less waste producer, I would say.
But now everything that we talked about relates to scientists. But the green chemistry or sustainability is not just ending here. It extends to policymakers, business leaders, consumers, and how do you, what can we say to them, to the non-scientists, that how can they contribute to this?
This is a quite important question in the sense that if the market, if consumers, and we all are consumers, are not aware of this will never be taken. But I think that this is nowadays, if we read the press media, we read things on the internet, we read things on the internet. I think this is already done. There is the awareness of many people trying to look for more sustainable items, products, and so on. And this is catalyzing also the establishment of more sustainable processes in industry, because people that are delivering these chemicals are being more and more asked by the final consumers, hey, how is the environmental print of your product? So then they have also to think in how to make this done. Of course, also from the regulations, this can be triggered or can be improved if we set some kind of regulations as a threshold of the amount of contaminants that we can put. I am more by the thinking of trying to combine an economically attractive process with sustainability. So there is a term that is called process intensification, which means that you try to make an optimization of the process to make more with less. And this works in the two senses. It works in the economics, because you are making more with less, but also in sustainability, in the sense that you are making less waste because you make a better use of the resources. So I think if we manage to get more and more of these combined cycles, combined with the end user vision on the things, which also has to do with the dissemination. So we are doing now that we are trying to bring this message to non-specialists, because we have to make them aware that chemical processes generate the waste, and we have to develop processes that make less waste to be more sustainable. So all in all, should go to this kind of system at the end. Or this is my hope.
It's very inspiring to hear about the potential of the field. We are coming to an end soon, but before we wrap up, what advice would you give to young scientists like us who are also passionate about enzymes, biocatalysis, green chemistry?
Well, I think that it's a bit to go back to the discussion we had in terms of always consider how green or how green your process might be critical with your own system, and try to make improvements on your reactions on the process that you are trying to make a better use of the resources, which are going to lead to less waste production at the end.
So never stop optimizing.
Yes, of course. I mean, but this is also in green chemistry, biocatalysis, but in general in life. I think we should try always with all the process to try to be always to do it better than the day before.
Thank you so much for joining us and sharing your insights. Your expertise and passion for green chemistry are truly inspiring. And to our listeners, we hope this episode has given you a better idea of how green chemistry works and how it can help solve one of the world's biggest challenges, problems. So we learned that whether you are a researcher, policymaker, or simply someone curious about the future of our planet, remember that green chemistry is a collective effort, and every small step counts.
Exactly.
Thank you. Thank you so much.
Thank you very much.